So, Samuel, you're talking about balancing short-term and long-term rewards. This movie or book example, it's relatable. But how do we actually measure that long-term value?
Exactly, Alfred. That's the crucial point. We can't predict the future perfectly.
So, no magic formula?
No magic formula. But we can estimate it. We learn to predict the future value of different choices by looking at past actions and their outcomes.
Like, looking at all the times you chose a movie instead of a book?
Precisely. And critically, we factor in the time value of those rewards.
Time value? Explain that.
Imagine a reward now is more valuable than a reward a year from now. We use a discount factor to account for this. Future rewards are worth less than immediate ones.
So, what's this prediction problem you mentioned?
It's about figuring out how good a specific strategy policy is for an agent.
So, if a policy is great, its future reward is higher?
Absolutely. We calculate this expected future discounted reward, and that's the value function. This prediction problem is key. Accurate prediction leads to better strategies.
And why is the policy only as good as the estimates?
Because if the value function estimates are wrong, the policy we develop is flawed. The more accurate our estimates, the better our policy.
Okay, I'm starting to get it. But what about the control problem?
That's about improving the agent's behavior. Using the value function estimates, we can adjust the policy itself to maximize future rewards.
So, we're not just predicting, but also optimizing the choices?
Exactly. We're learning to make the best possible choices, considering both the short-term and long-term impact.
This sounds like a complex process. What if the movie or book example was wrong? I mean, sometimes a movie is the perfect thing I need.
That's valid. The model is only as good as the data. In reinforcement learning, this is a constant challenge. Our models work better with more data and more diverse choices.
So, it's iterative learning?
Yes, iterative. We adjust our strategies based on experience.
So, Samuel, you're saying there's more to estimating policy value than just running the policy repeatedly?
Absolutely. That's a valid basic approach, but there are tons of more sophisticated methods. Imagine trying to figure out a good route for a delivery service. Just driving the same route repeatedly won't find the best route.
Right. So, you need to find a better way, like maybe a different route?
Exactly. Different approaches offer different strengths and weaknesses. Some are like opposite strategies, but there are also strategies in between.
Like what? What are these other approaches?
We'll explore various methods later. But first, let's get clear on rewards, returns, and value functions.
Okay. Rewards, returns, value functions. Sounds important. Explain these.
Rewards are immediate feedback. Think instant gratification. Returns are the sum of all future rewards, taking into account how important future rewards are compared to immediate ones. This is discounting. Value functions are the average return the agent expects from a given state and policy.
So, returns are like a longer view of things?
Yeah, the total discounted rewards. A better measure of long-term performance, especially in situations where immediate reward might lead you astray.
Like what? Give me an example.
Imagine eating a lot of candy now. Immediate reward, high sugar rush. But the return? A tummy ache later. Value functions consider all possible future consequences.
So value functions consider all possible consequences, right? What about the random walk environment you mentioned?
The random walk is a simple model, but it's very useful for exploring different reinforcement learning concepts. In this case, the agent can't control the outcome. The reward, and the returns, are all random. The agent needs to learn the value function for the given policy even though the actual path is random. The goal is to figure out the expected return, regardless of the random path.
Wait, so you're saying the agent's goal is not to control the walk, but to understand the random outcomes?
That's right. The agent's goal is to maximize the expected total discounted reward given the stochastic nature of the environment and policy.
I get it now. So, the agent's goal is to maximize the expected return, not the return itself.
Precisely. It's about understanding the long-term average outcome, not just chasing immediate rewards. This idea of balancing immediate reward and long-term outcomes is really key to reinforcement learning.
Okay, Samuel, we're talking about Monte Carlo methods, specifically first visit versus every visit. Can you clarify the core difference?
Sure, Alfred. The key difference lies in how we handle multiple visits to the same state within a single trajectory.
So, if we're tracking returns, we have to decide if we only use the first visit to each state or all visits.
Exactly. First visit MC, FVMC, only uses the return from the first visit to a given state in an episode. Every visit MC, EVMC, on the other hand, averages returns from all visits to that state in the same episode.
Interesting. So, what are the pros and cons?
FVMC is simpler, and its convergence is easier to prove. The returns are independent, like flipping a coin many times.
Independent? So, each visit to a state doesn't depend on what happened before?
Right. Each visit is an independent data point. This makes the math simpler.
And EVMC?
Well, returns aren't independent in EVMC, as subsequent visits depend on the trajectory. But with enough data, EVMC still converges.
So, practically, what's the impact on the estimate's accuracy?
In most cases, the difference isn't dramatic. Both methods are valid, and both will provide estimates that get better as you collect more data. You'd choose one over the other based on simplicity or speed requirements.
Got it. And how does this concept manifest in the code snippets?
The first underscore visit variable in the MC underscore prediction function controls this. If first underscore visit is true, it's FVMC. If false, it's EVMC.
So, the code is actually choosing the method based on that flag?
Yes. It checks if a state has been visited before in the current episode. If so and it's FVMC, it skips that state.
I see. You mentioned convergence. What does that practically mean in the real world?
As you gather more episodes of data, the estimate for the value of a state gets closer and closer to the true value. It's a crucial aspect of any reinforcement learning algorithm.
So, any potential pitfalls?
Using EVMC may slightly increase the computation, as you need to keep track of all visits. But it might also be slightly more accurate in some cases, especially with more complex environments. One common misconception is that FVMC is always better or always faster.
What's the real-world benefit of these algorithms?
Imagine training a robot to navigate a maze. Using these algorithms, we can estimate the value of being in different locations in the maze. That helps train the robot to make better decisions.
Thanks for breaking this down, Samuel. It's really helpful. So, Samuel, you're saying there's a spectrum between Monte Carlo and temporal difference learning? How does that work exactly?
Yeah, there's a whole range of possibilities in between. MC is all or nothing, waiting until the end. TD is like taking a quick guess and adjusting. There's a middle ground.
So, we're not waiting until the end of the episode? What's that in between look like?
Exactly. You can wait for 2, 3, even 4 steps. You're bootstrapping, but not quite as aggressively as TD. It's about finding the right balance.
And why is that balance important?
Well, MC is great for knowing the actual return, but it's a lot of data to gather, high variance. TD is quicker, but can be too quick, leading to bias. This in-between approach lets you control how much you're relying on predictions versus actual rewards, reducing bias and variance.
So, more steps means more reliance on predictions?
Precisely. More steps means a stronger bootstrapping signal. It also smooths out those noisy, unpredictable rewards. Imagine a game where rewards are really rare. MC would need many episodes to get a good average. TD might get lucky with an early reward and miss the long-term reward. A more intermediate approach can get the best of both worlds.
Interesting. So, this midpoint is essentially a tuning knob?
Yeah, absolutely. You can tune how many steps to look ahead before calculating the expected return. It's a trade-off. Faster, but slightly less accurate estimates versus more precise, but slower calculations.
Makes sense. But, is there a way to figure out how many steps to look ahead a priori?
You know, that's a really tricky question. Usually, it's an element of experimentation. Try different numbers and see what gives you the best performance.
And that's where the personality comes in?
Absolutely. MC agents are all about the payoff. They're businesslike, outcome-focused. TD is about gradual adjustment, more relaxed and reflective. This middle ground offers agents more flexibility. More like a sensible, well-rounded approach.
Okay, Samuel, we're diving into in-step TD learning. So, you're saying this is like a compromise between Monte Carlo and temporal difference methods?
Exactly. Monte Carlo waits until the end of an episode, which can be really long. Temporal difference learns after just one step. N-step TD sits in the middle.
So, it uses a finite number of steps?
Yeah, instead of the entire episode, or just one step, it uses n steps to calculate values. It's like, let's see what happens in the next few steps, then update.
Okay, so how many steps and is optimal?
Well, there's no single magic number. Sometimes, the optimal value sits somewhere in the middle, not at either extreme. It depends on the specific task and environment. You might find a good value of n through experimentation.
That makes sense. Now, you mentioned a target value. How is that calculated?
We calculate the discounted return over those n steps, plus the estimated value of the next state, also discounted. That's our target value.
So you're incorporating future predictions, in a way?
Exactly. We're combining immediate rewards with the predicted value of the future states. That's why it's called bootstrapping.
So why would you use this approach?
It balances the speed of TD with the accuracy of MC, essentially. It's a nice middle ground that offers a better balance between computation time and a high accuracy prediction.
In your Python code, you were talking about a decay schedule for the learning rate. Can you elaborate on that?
It's like slowly lowering the learning rate as training goes on. We start with a big learning rate to quickly adjust estimates, then we slowly shrink it. It lets the agent focus more on refinements as it gets more certain about its estimates.
That sounds good, but what happens if, at any point, you hit a terminal state?
The code handles that. We just use the rewards and values until the end step or the terminal state is reached. The target value calculation just stops and uses the appropriate rewards and values, so the agent still learns in this case. It gets more efficient by handling these conditions appropriately.
That's a good point. So, are there any potential downsides to this n-step approach?
Well, the n parameter can impact performance. You need to find a good balance to avoid over or underfitting. So, experimentation is key.
And troubleshooting? Say, the algorithm doesn't seem to be learning effectively. What would you look for?
I'd check the n value. If it's too high, the agent might not learn quickly enough. Too low, and the agent might not incorporate enough information. The discount factor gamma can also be a problem. If it's too low, the agent will overemphasize immediate rewards. Also, the learning rate, the decay schedule for the learning rate, those can all make a difference.
Fascinating. So, n-step TD blends the strengths of both approaches. It's not just theory, it's a powerful tool in reinforcement learning.
Precisely. It's a valuable technique for agents in complex environments, offering a reasonable trade-off between speed and accuracy.
So, Samuel, we've been talking about TD, this advanced temporal difference learning. What's the big deal about eligibility traces?
Eligibility traces are key, Alfred. They let TDA learn much faster than regular TD.
Faster? How does it work? More data means faster learning, right?
Not quite. Regular TD waits until the end of an episode. TDA is different. It updates after each step. Crucially, it focuses the update on the most relevant recent steps.
How does it do that? It sounds like magic.
It's all about eligibility traces, those memory vectors. Imagine a short-term memory for recently visited states.
Okay, so it remembers where it's been recently.
Exactly. Each visit to a state bumps up its eligibility. Think of it like a reward that's not just for the immediate step, but for the recent steps, decaying as they get further in the past.
So if a state has a high eligibility, it gets a bigger update?
Precisely. The update calculation is multiplied by the eligibility. States visited recently get a bigger weight, effectively. That way the most recent experiences have a bigger effect.
But how does it decay? That's crucial.
Yes. The eligibility decays over time, controlled by these parameters, lambda and gamma. So, less weight is given to states that were visited long ago. Imagine, Alfred, you're walking a maze. The most recent turns are more important to learn than the first few.
So, it's a weighted average?
Exactly. This means less variance in the value estimates because it discounts older actions.
So, if lambda is 0, it's just standard TD, right?
Correct. No eligibility traces, only the immediate reward matters.
And if lambda is 1, it's like Monte Carlo, right?
Almost, but not exactly. If lambda is 1, and updates are done at the end of the episode, it's like Monte Carlo. But, in real-time online learning, they are different.
Interesting. So, the bias-variance trade-off is crucial here?
Absolutely. We're finding the best balance between a slightly biased but smooth estimate with a less biased but potentially noisy estimate. It's a constant challenge. It's not just about speed, but also about accuracy.
That's a lot to take in. What about the practical applications?
TDA is used in many real-world applications where we need to learn policies quickly. Think robotic control, game playing, even financial modeling.
Very cool. Thanks, Samuel. Really helpful. Okay, Samuel, we've talked about sequential and evaluative feedback. So, how exactly do these two challenges combine in reinforcement learning?
Well, think of it like this, Alfred. Agents in RL often need to balance immediate rewards with long-term strategies. At the same time, they're gathering information about the environment, but that information's not always perfect.
So, gathering information while prioritizing rewards is like trying to learn a complex recipe while blindfolded, right?
Exactly. It's a tricky juggling act. Reinforcement learning is all about figuring out the best actions to take given these two constraints.
You mentioned Monte Carlo and temporal difference learning. Can you give a quick overview?
Sure. Monte Carlo methods are like relying on trial and error, gathering lots of data to estimate the value of actions. TD learning, on the other hand, uses the current data and learned estimations to predict future rewards, a bit more like an educated guess.
So, the in-step TD agent sits somewhere in between these?
Exactly. It's a flexible approach, adjusting its estimation based on the number of steps it takes into account.
And then there's TDA. What's that about?
TDA combines both approaches, sort of like mixing Monte Carlo and TD learning. A single agent can account for immediate and future rewards in more sophisticated ways, handling varying data availability.
Wow, that's a lot to consider. Are there practical applications of these methods we should know about?
Definitely. Games, financial modeling, and even optimizing supply chains. These agents are pretty adaptable, once trained well.
Interesting. What about the time step limit you mentioned? How does that affect these algorithms?
It's crucial. In real-world applications, often you have a time limit within which an agent needs to take actions. Simple algorithms might miss out on evaluating long-term goals if they're capped by these limits.
How can we make sure algorithms are robust enough to account for this?
We need to adjust these algorithms for those time constraints. It forces more meticulous calculations about the short-term and long-term impact of their actions. Adjusting them takes a bit more careful tweaking to provide more accurate estimations.
Great points, Samuel. So, what are the exercises you suggest? How can we delve deeper?
You can modify existing algorithms to account for time step limits. Compare and contrast different methods like Monte Carlo, TD, and N-step TD, visualizing how their estimations change under different parameters.